Hello, hello. Welcome. Exam revision. We have done all the content, at least as far as Class 2 is concerned. We've done all of the Unit 3-4 content. And now you get to have a look at the exams. Might be the first time, actually, that you've seen an exam paper for the methods. For whatever reason, they did a really yuck, pale pink thing attached to the side of these now. They've changed the look of the exam significantly since last year's. Sorry, this is 2024's, but like since the previous year after that, they changed the look of it, and it makes it look significantly worse for some reason. I don't know why they felt compelled to put effort into making it worse, but here we are. But yeah, so I guess pretty much all these are going to look like is we'll basically go top to bottom, reasonably speaking, on the questions, and then just sort of maybe talk high level if people are getting the concepts well enough, or diving into more specifics where necessary. You'll find specifically with the tech-free ones, questions tend to repeat themselves in their relevant positions a lot. Like for instance, question 1A and B are always going to be something diff related. Question 2 is pretty much always, if not a follow-up with anti-diff, going to go into something like simultaneous equations. Then you get some sketching stuff. In this case, you got some sort of truncus going on. They'll ask a few follow-up questions on that. Question 4, I believe, is pretty much always some kind of probability thing. It's a baseline type probability thing. In the sense that I mean, like they only ask a few questions about it, not like a million of them. Question 5 is sort of whatever it wants to be. Same with question 6 and 7. Sometimes probability will make an appearance again, although it looks like in this case it only made one appearance. Oh no, it had one here. This was probability. They had a confidence interval thing under here. So there's some variance as far as how the questions are asked, but a decent number of them are quite repetitive, and that's pretty much the go here. So for the most part, we're working out of the screen share, and then where necessary, we'll dive into some more in-depth working out for them. So without further ado, we can dive right into it. So question 1, find dy and dx. What are we thinking when it comes to finding derivative?
Rule involved in here.
I think it cut out a little bit the start of your sentence. Could you repeat that?
There's going to be a product rule involved.
Yeah, correct. Product rule. Right, we've got a product of two functions. Product of e of x multiplied by cos 3x. Absolutely. Yeah, in fact, maybe for the first time we'll just sort of go through even the simpler questions, and then as we'll get more familiar with them, we can maybe gloss over them later. So product rule, once we identify our two functions, what do we do with that?
We multiply one of them with the derivative of the other, and then vice versa, and then add them together.
Yeah, correct. So basically going to identify what our u and v terms are. Those are going to be the two functions. So if we go to the handwritten section, we'll see we have u equals e to the x, v equals cos 3x. Then, as you said, we need derivatives of both. So diff of e to the x is just e to the x. Diff of v dash, what's special about this? What's technically required for doing derivative of v?
Is this going to be like a chain rule?
It is a chain rule, technically speaking. I will say if we scroll down to the formula sheet on the PDF on the screen share, it is, yes, a chain rule, but also a chain rule that's told to you already on the formula sheet. So diff of cos ax is just negative a sine ax. So you can just read it directly off your formula sheet. Worth highlighting, it is technically a chain rule. But yeah, that's going to give us negative 3 sine 3x. And then, yeah, as you said, the baseline of one gets multiplied by the diff of the other. So if you line out your working as I've done in the handwritten section, you'll basically just draw lines to signify that you're multiplying across those diagonals. So you're going to have negative 3 e to the x sine 3x, and then it's going to be a plus between them for e to the x cos x. That's that diagonal up one. As far as going from here, you could factorize e to the x out if you like. Doesn't really change much. Maybe the only thing I'd actually put in there is specifically saying dy on dx for that, because the question says find dy on dx. If you put f dash, that's not necessarily wrong. You'll still get the mark. It's more so if you're shooting for those higher level study scores. If you're on the boundary of getting one versus not getting one, these are the things the assessors use to determine whether or not someone's going to get that boost or not. Yeah. And then, yeah, as far as product rule, what we just did there, that is on your formula sheet, so that's not something you have to have memorized. Product rule, if you have a look at the screen share, it's detailed. I hope you guys can you guys see my cursor on the PDF? Yep, okay. Yeah, so there's your product rule. Derivative of a product of u and v is u v dash v u dash. So that tells you what things you need. That's that. Part B, only slightly different. You've got f of x, find f dash of 3. What's going on there?
Well, first we're gonna find the derivative of that function, which I think we're going to use the chain rule.
We are going to use the chain rule, yeah. So, because I didn't really highlight it earlier, we use chain rule basically whenever we don't have a basic function, like natural log x would be the basic version of this. For this one, cos x would be the basic version of that. You use chain rule whenever you have something else, a composite function. So yeah, chain rule. How does that work?
Um, because this is a log, do we do the derivative over like what's inside the log?
Yeah, exactly. Derivative over what's inside the log. Derivative of what though for the numerator?
Of what's inside the log, so
Of
it'd
what's
be
inside.
like, yeah.
Yeah, precisely. That's real good. The way I typically like to write this out is completely generically for any chain rule, which is you start by defining your u, which is the inside of the log in this case, x cubed minus 3x plus 2, and then you can get your derivative of that. So looking at 3x squared minus 3. From there, I'll typically write y of u just to remind myself that I've done the substitution. And then, once you do your y dash of u, we know that's just going to be 1 over u. You can read that directly off your formula sheet. Completing the chain rule is the multiplier of this, which is why this ends up being in the numerator, and the denominator ends up being whatever's the bracket of the log. So that was a very specific result for the log. This is how you pretty much do it if you want to have a general approach for any chain rule ever. So you end up having, now we're going to say specifically f dash x, not dy dx for this one. You have 3x squared minus 3 divided by u, which we know is x cubed minus 3x plus 2. Sweet. That's not quite the finish of the question though, although it will get us 1 mark. What do we do now?
We just sub in 3.
We just sub in 3. Correct. That's it. F dash 3. Every x is going to get a 3. I can do that if you want to see it, but we're just simplifying some algebra there. So if someone wants me to simplify that, speak out. Otherwise we can move on to the next thing, which is simultaneous equations. So have a read. let me know how you might start a question like this off of. Even if you don't have like a concrete first step, what kinds of concepts are coming to mind when you see a question that's written in this way?
For this question, I would first like rearrange for y for both.
That sounds like a great idea. Yeah, rearrange for y in both of them. That's what I've got written in my approach to how I do it as well. So just for the sake of it, we'll call this one equation 1, we'll call this one equation 2. You'd put the negative on the 3kx and divide by negative 2. So you're looking at y equals negative half at the front of k plus 4 minus 3kx. And then finally, you're going to have y equals, how are we going to do this? We'll do it y equals mx plus c. So we'll bring the, I'll have 3 over 2 kx, and they're going to have negative k plus 4 over 2. That way you have a full y equals mx plus c from that. That's our equation 1, and then equation 2, a very similar thing. Subtract this, divide by k, so we're looking at y equals 1 over k, still got the negative k from before, minus bracket k minus 4x, and then again, just for simplicity, we'll rewrite it as y equals mx plus c. So that's going to be negative bracket k minus 4 over kx minus k over k, so minus 1. That's equation 2. All right. If that's clear enough how that was created, what can we do from here?
Since we got y isolated on both sides, can we just like make equation 1 equal to equation 2 and like that'll remove the y's?
It will remove the y's if you do that, yep. You'll be left with both k and x in your solution, which is going to pose a bit of a challenge there. I don't know of a way that you can then go from there. So unless, do you have an idea of how you would take it after there?
I don't know the exact step, but I was figuring that since k is a constant, maybe if we like isolated kx's and the numbers, and we would find what k is. But since we don't have x, that probably isn't viable.
Yeah, we need to find a way to get rid of x out of the whole thing, both x and y.
What I do usually for these ones is I take everything that's before x, because that would be like the gradient, and I equal it to each other. And then I'd do the same for like what c would be, which is everything after x, kind of.
Yeah, that's a great idea. So I know where you're going with it. Considering that we're looking for no solutions, what are you trying to achieve by doing that?
We want them to not equal each other. Sorry.
Not like what not equal each other?
Like the gradient and c to not equal each other, because then they never intersect.
Yeah, correct. I'll put a slight nuance on that. Only one of those variables, gradient or y-intercept, which one of those is the only one that actually matters as far as not touching each other?
Is it just c?
Wait, sorry, what am I saying? No solution. No solution is parallel. No, so you do need both, actually. You need... Because no solution means parallel. So when we think about parallel... Sorry, I was thinking of... what was I thinking of? Unique. Yeah. So no solutions mean parallel. What does that mean we have to achieve?
Same gradient, different C value.
Yeah, there we go. Sorry for the confusion on that one. So same gradient, so these two red boxes need to be the same because those are the gradient terms. 3k over 2 is equal to negative bracket k minus 4 on k. That's going to get us same gradient. You can also set up your equation with the plus c terms to say that those need to be different. You're probably better off doing these one at a time. Because the simultaneous, if you just do these, they can take a bit of time to get an answer from. Like for instance, this one's going to be a quadratic once we do our simplification. You just sort of cross multiply, you're going to get 3k squared equals negative 2k minus 4. 3k squared equals negative 2k plus 8. 3k squared plus 2k minus 8 equals 0. Like, you're just solving a quadratic here. You've got a bunch of different options how you want to do that. There might be a factorized approach you can do here, where you take out the 3 from here as a factor, and then find two things to multiply here, add to give here. Or you could just do quadratic formula to get your answers. Does anyone want to see one of those approaches, or should I just cas this out to save some time? Cool. All right, cas it is. So based on what I'm seeing, both of those would have worked. So you would have had k equals negative 2 or k equals 4 on 3. Whenever I see a fraction that's nice, it usually means some sort of factorizing can be done. When there's not a nice thing, you get roots here instead. Those will be the two possible k values, specifically the two possible k values that mean gradients are the same. And so what you'll often find is one of these gives you also same y-intercept, and one of them gives you a different y-intercept. There's a couple of ways you can figure out which is which. Any thoughts on what you might do?
Wait, sorry, what was the question?
Yeah, so we've got our k values that are possible for gradients being the same. We now need to figure out which of these will also give a different y-intercept. What are some potential things we could do to figure that out?
Do we just find the possible C values?
Yep, that's totally one way to do it. You could do the exact same thing we just did there. You grab the two C values, make them equal to each other, and then, well, technically you could use a do not equal sign if you wanted to be very specific with it, but using a regular equal sign isn't so bad as long as you remember that you're trying to do a not the same. Yeah, that's a very standard way of doing it. You just have to repeat exactly what we just did. And this wouldn't take long at all. It's linear. Negative 2 equals k plus 4. K equals negative... Hang on, what? Did I do it dumb? Maybe I cas this out wrong. Or rearranged it incorrectly. Usually there's a pair here. Let me just check the answer to make sure. All thirds and negative 2 is correct. What did I do stupidly here? Negative k on k is negative 1. And... oh, I didn't put the negative sign in here. So that's going to make it positive 2 over here. And then we're going to get negative 2. Okay, that makes more sense. So we see that we have k equals negative 2 on this side, k equals negative 2 on this side. So if we think about our criteria that's required, which is same gradient, different y-intercept, what's our conclusion?
A is equal to 4 on 3.
K equals 4 on 3, yeah. That's the only one that has m being same, but y-intercept being different. Nice. This one ended up being pretty easy to do a rearrange for, except for the fact that I forgot to put a negative there. If you have a more complicated set of C terms, one of the things you can do is actually just plug in one of these K values back into these equations, but that's usually more complicated. It's really just a matter of what makes more sense for you. Because when you plug the only thing you'd actually have to check is in here, really, because you want to see if I plug in K equals something here, do I get -1? If yes, then bad. If no, then good. Which is, yeah. Anyway, that's that. If there's anything to clarify further, be sure to sing out. Otherwise, let's have a look at question 3, which is a graphing question. I guess one of the first things to identify is what kind of graph are we graphing, and then from there we can figure out what the steps will be.
Chris, this is a truncus because obviously like it has the brackets and squared at the bottom, and I'm guessing that's why the domain doesn't encompass -3 because that's probably its vertical asymptote.
Sure is. Yeah, very good. So that's one key feature we can write down immediately now. We can see that -3 is going to be its vertical asymptote. So let's get that one down. Nice. And yeah, just to highlight that again, we know it's truncus because we have 1 over x squared. Yes, there's a translation in there, but still just something squared on the bottom. Yep, all right, got vertical asymptote. What else do we need to do for the proper sketching of a truncus?
Find asymptotes and horizontal. Find asymptotes and intercepts.
Yep, all right. Which one should we go for next?
Well, we can see like the horizontal asymptote is going to be at y is equal to -2 because
Yeah,
it's the translation.
that's it. Whatever the vertical translation is ends up being your horizontal asymptote. That's going to give us a nice little grid to work off of. All right, you mentioned intercepts, so we could do that next. What are we going to go for first? It really doesn't matter what order you do these things in.
We can do g of 0.
G of 0, yep. So that's something at x equals 0, which means you're doing the y-intercept. Y equals 1 over 0 plus 3 all squared minus 2. Y equals 1 over 9 minus 2. Y equals 1 over 9 minus 18 on... Wait, sorry, that's not how that works. You want a 9x. What am I doing? Why am I freezing on this? No, that's right. 9. 17 on 9. That was weird. I don't know why I froze on that. Minus 17 on 9. Cool. Y-intercept. And x-intercepts. What do we do there?
We make y 0 and rearrange for
Mhm.
x.
That's it. 1 over x plus 3 all squared minus 2. 2 equals 1 over x plus 3 all squared. We're getting yet another quadratic here. 2x plus 3 all squared is equal to 1. You know, you just expand that out and simplify. That'll take a little bit, so I'll just cheat that out on the CAS unless anyone wants me to actually do it by hand entirely. Okay. X plus 3 all squared. That's 1. Yeah, it's going to get us... Geez, it would have been a quadratic formula too. So you're going to have -3 plus minus root 2 on 2. And then, well, yeah. The plus root's going to go here. The minus root's going to go here. So, just copying those down in those spots. Then all we're going to do is draw the curve, which that's kind of hard to describe verbally, so I'll just kind of do it for you, which is you want to have a sort of tree trunk-like thing. Maybe I should have drawn my intercept down here, so it would have actually looked anywhere halfway decent. And then, yeah, just label that point down there instead of where I put it before. Oh no, killed the wrong thing. There we go. I guess there's a couple of reasons why it has to point up. One is because that's where the x and y intercepts are, so they have to point up. But what's the other mathematical reason why it points up instead of down? Anyone know how to know at a glance whether a trunkus points up or down?
Is it like if the x has, or the x or y has a negative?
One of those, yeah. Which one is the important one?
Is it the x in this situation?
So as in, do you mean like if it was negative x plus 3 all squared?
Yeah, or like negative whenever, like x plus 3 squared.
Well, those are different things. If the negative is in the brackets of the x, that's a horizontal flip.
Yeah.
Whereas if the negative's on top, that's a vertical flip. So the one that we want specifically, if it's going to point down, is a negative on top. Unless you meant the negative outside the brackets, in that case, it doesn't matter if it's top or bottom. That's still going to be vertical if it's outside the brackets. But yeah, that's that. Next up, determine the area of the region bounded by the line x equals -2, the x-axis, the y-axis, and the graph. Yeah, I won't give any hints off of this one immediately. Let's see what you guys can come up with. Area bound.
Chris, will this be like an integration over a limit?
Yeah, integration over. So using the word limit, I know what you mean by that. A limit technically implies like a diff type thing.
Yeah.
But yeah, I know what you meant. You would call those the terminals of the integral, or I guess because you're integrating, you would say you'd integrate it over a domain. That might be another way of framing it if you wanted to. This is more so if you have to write down what you're doing. But yeah, anyway. So with that in mind, how do we figure out the domain over which we're Sorry, I'll take a step back. Integration over a domain, you're doing definite integral. The reason why is because you're doing area under a curve. That's for everyone else, if everyone else wasn't up to speed on that. Area is always integral. Now that we're clear on that, how do we actually figure out the upper and lower bound of our domain based on the information provided?
We're gonna want to see like where x equal -2 intersects with the graphs.
Yeah, certainly, because we got this plus root, which I kind of just sort of threw there. We have to roughly estimate how negative this number is. We got a root in there. So I guess our question is this going to be more negative than -2? Like, is it going to be left of -2, or is it going to be right of -2? And how could we estimate it? That's really close.
I think root 2 on 2 is a little bit less than 1, so so that means -3 plus 1 would be -3 plus root 2 on 2 would be -2 point something.
Yeah, it's actually so close. If I just cast it out to make sure I didn't say the wrong thing, it's -2.29. But yeah, no, you're right. Root 2 on 2 is a little bit less than 1. So root 2 is going to be approximately 1 point something or other. I think root 2 is usually like 1.4-ish. And then when you halve that, basically, as long as you know root 2 is 1 point something, even if you say like 1.9, whenever you halve a really big 1 point something, you still get into a decimal 0 point something. So no matter how high you overestimate that, you still fall to the left of -2 rather than to the right of it. But that's the gist of it, really. Approximating and saying, okay, root 2 is going to be roughly 1 point something. Halve that, we're going to end up being slightly left. So this root was slightly left of -2, so -2 is actually here. So I guess I'll do that in green just so we can see the contrast a bit better. Okay, so that tells us the line x equals -2. Now that we know that, there's other information there that could tell us what the shaded area is going to be calculated with.
So would we want to do g of -2 to find like the y of where it intersects with the graph? And then obviously like the rest is just the little bit in the corner.
Oh, okay. So yeah, that second bit that you said. So the stuff that you want is in the corner. Yeah, the first bit about finding the y value here, you don't actually need y, because when you think about doing definite integral, you just need x information. You need where do I start and where do I end as far as x is concerned. Everything
Okay.
else is handled by the definite integral. But yeah, the reason why it's this bit in here is because it says region bound by x equals -2. So that gives us this little endpoint here. The x-axis, so that's this bit, that gives us an upper for it. The y-axis, so that gives us the horizontal endpoint. And the graph, g, so that gives us the bottom of the shape. And so those four things combined are going to give us our total desirable area. So now the question is, if you want all of this, it's just definite integral from -2 to 0. That's part of the answer here. There is a bit of a nuance you have to put on that. You're integrating from -2 to 0. What do you have to do when it says bound area?
We have to like say unit squared next to it.
Yeah, that's one thing you can do to enhance your answer. Wasn't what I was quite looking for, though. It's something more mathematical you have to do to get the right answer rather than the wrong answer.
Is it like put a negative out front because you're finding negative area, or?
Yeah, so whenever it's area bound, they want it to be positive. The only time you ever consider negative area is when they say find the signed area or literally find this definite integral, and they don't even say area at all. Those are the only cases where negative area is actually allowed. And so because this is area under graph, it's considered negative. We want to slap either a negative sign on the front of the integral or flip the terminals, whatever you like doing better. You do need to know both though, because it's a very likely multi-choice question, which will be some nasty set of bound area stuff, and they'll do both in there. So my preference has always been doing a negative on it. So your bound area, you might just call it A for area, is equal to the negative of going from -2 to 0. Let me just remember that. Yeah, -2 to 0 of the function g of x. I'll just write g of x instead of writing the whole thing. And that's actually it. Yeah, nothing else. It's just area under because there's no other curves to consider in there. Does anyone want to refresh on how to do definite integrals? Like, how do we do this?
Yes, please.
Yeah, certainly. In fact, yeah, this one is going to be a bit of a fun one too because it looks like something you can't integrate unless you rewrite it in a certain way. So we've got -2 to 0, and we've got g of x, which was 1 over x plus 3 all squared minus 2. First thing to do for definite integrals is antidiff the inside. That's going to give us, well, I kind of already called it capital A, so maybe we'll call this, yeah, I don't know. We'll still call it capital A of x. Antidiffing this. Does anyone know what you have to do to antidiff this?
I'm not 100%, but like should we like expand the bottom first and then bring it up, or like I don't really know.
Expanding the bottom and then bringing it up would put a negative index on the entire thing. Then you're running into what is essentially a chain rule situation, but in integration. And in methods, you don't actually, well, my notes kind of cover how you can do it a little bit, just in case. But something like that is probably a little bit too complicated to reasonably do in methods. It is mathematically doable, what you're describing, just not to a math method standard. What's better is instead of expanding it out, you still want to do your flip to a negative index, but just before you do a expansion here. So actually before we write a of x here, we can start by rewriting our integral again. It's going to be from -2 to 0. We're going to have x plus 3 power of -2 minus 2. Now that we have that, there is a formula sheet thing we can look at for the integration of this. It is still technically a chain rule type thing, but it's one that the formula sheet has told us how to handle, which is, if we have a look back at the screen share, whenever you have ax plus b to the power of n, which we do, we have x plus 3 to the power of -2. The anti-diff is, well, as you see in the screen share. So that's what we're going to do. So capital A of x. So in this case we have, I'll even write it out, we got n equals -2, we got a equals 1, and we've got b equals 3. That's all we need. So when we put them all in their spots, we should have 1 over a bracket n plus 1, so -2 plus 1, times ax plus b, which is just our x plus 3, n plus 1, so -2 plus 1. That's this portion of it. There's also the -2 involved. That one's a bit easier. Can anyone tell me the antidiff of -2?
Is it just -2x?
Yeah, -2x. That's it.
I'll see.
And then yes, plus c at the very end. We only do one of them, even though there's two functions in there. Yeah, and then we're just going to simplify that down. Oh, I just realized I was off center there, sorry. X is equal to, so you got negative, yeah, just negative. X plus 3 power of -1 minus 2x plus c. Cool. All right, that's our antidiff function. Does anyone know the next step after you antidiff when you're doing definite integrals?
Do we have to substitute the terminals and then subtract?
Yeah, correct. Do you know what order you do them in? Like capital A of what minus capital A of what?
I don't know if it's like in this case, I think it's we do the -2 first, the bottom terminal. I'm not sure though. Like I haven't done this.
You can do that, but you have to change something ever so slightly. Yeah. Yeah, go ahead. You got a speaker still?
No, I've got no idea now.
Should we just do the 0 and then minus the -2?
Yeah. So if you're just doing stock standard integrals, you would do top take bottom.
Awesome. I just have another question, just because in this scenario, do we would we lose a mark if we didn't do the plus c because it's the error, or would it be okay?
No, yeah, you'd be fine because you're doing definite integral. It's not gonna. Now, this is like a thing that you'd put in there if you want to be, if you know you're going to be on the edge of a study score increase, or if you worry that you'll be on the edge of a study score increase. Because, I mean, the reason why I highlight that is because a lot of people will get the same mark on a test, same percentage, and so these are the things assessors will use to differentiate between people. So putting a plus C on it is probably slightly more favorable. What is definitely not required is to put the plus C in further working out, because you know those are going to cancel down anyway. But yeah, okay, so you're doing it's always top take bottom as far as integrals go. The reason why I say you can technically do them backwards is if you just pretend this negative doesn't exist when you do your final answer, because negative would also flip these terminals. but they're probably a bit complicated, so we'll just stick to this. Capital A is 0, that's pretty chill. So you got negative bracket 3 to the power of negative 1 minus, well, 0. I like to put square brackets around each of these terms, that way I don't forget where I am in the solution. Then you're going to have negative 2 plus 3 to the negative 1 minus 2 bracket negative 2. And again, we can just sort of forget about that plus c. 3 to the negative 1 is just a third, so you're going to have negative a third there. We're still going to leave a minus at the front. Negative 2 plus 3 is going to get us positive 1. Flipping that does nothing, so you still leave it as 1. The negative out here is going to come in. Negative 2 are going to make positive 4. And then, well, yeah, this is... I don't even know why I'm still going. Negative a third. Got 3, so negative 3. Negative 1 minus 9 on 3. Negative 10 on 3. And then, yeah, I guess chucking in units squared there can't hurt. In fact, yeah, I got the answers here. Do they bother with that? Yeah, they just leave it as the value. Now that gives us the definite integral. Reminder that we had negative of the definite integral. So just making sure when you give your final answer, therefore negative of that gives you to 10 on 3 units squared. Cool. All right. If there's anything to clarify further on that, let me know. Otherwise, we can jump on to the next one. Here we go, probability. This is some of the recent stuff we've been doing. X is binomial around a variable. I haven't explicitly said what this notation is. Does anyone know, just because they've done it before, what this notation means?
Does it tell you the probability of success as well as the number of trials?
Sure does, yeah. N is the first element, and then P is the second element. That'll be pretty obvious. N has to be an integer, and P has to be a fraction. So that's not so bad once you know it's talking about N and P. Yeah, stock standard, find the standard deviation. You don't have to have that memorized, it is on your formula sheet. But out of curiosity, does anyone know what it is?
Is a standard deviation just the square root of variance?
Square root of variance, yep. Does anyone remember the variance equation? Again, you don't have to. I'll pull it up because it's on the formula sheet. Just test some memory. Nah, all good. NP1 minus P. That's what we're doing. N is 4, P is 9 on 10. Plug in, and then you've got your value. Now, standard deviation, use the Greek letter sigma, or if you can't draw it like I can, like I can't, you might do SD for standard deviation. That's about it. Next up, find probability of x being less than 2. We don't need part A's answer for that, so unless anyone wants to see it, I'll leave that there. Part B, probability x less than 2. What's that all about?
I'm not 100% sure, but do we just put it in that formula where it's like 4 choose, well, in the scenario it'd be like 4 choose 2, the probability of success squared minus the probability of failure?
Yeah, it's kind of that. Just so I can make it easier for you to figure out where the terms would go. Here's the equation that you're talking about, which is probability x equals x is this, and here's your n over x, the n choose whatever. we're doing x less than 2, though. I will point that one out. So if we're doing probability x less than 2, this isn't a less than sign here, this is an equal sign. So if we think about what domain x less than 2 covers, what x values are for x less than 2 when we consider discrete?
Do we just do like this like probability of x equals 1 in this scenario?
That's one of them, yeah. There is actually another one in there. I'll go back to the actual question. Because we got to remember that, well, actually there was no context given here. They just didn't really say what the scenario was, just that it was binomial. Discrete can go to 0. One common example would be like coin tosses, right? You can get 0 heads out of 4. So since 0 is one of the possible options, you're essentially doing the addition of x equals 1 and x equals 0. Yeah, both of which are done with Bernoulli sequence. That was the equation I pointed out here. I already know that. Well, yeah, I'll write down. So we had it was n equals 4. It was p equals, I think it was 9 on 10. Whatever. I'll refresh that if I need to. And then basic probability x equals x is going to be n factorial on n minus x factorial, x factorial. Yeah, we'll do it this way. P to the x, 1 minus p to the n minus x. Now, did I remember that properly? Sure looks like it. Awesome. All right, back to the actual question. Let's see if I remember the n and p properly. I did. Awesome. Yeah, so we're just going to be subbing in our n's and p's into both versions of this. So we want to do probability x equals 0, which means every x is going to get a 0. And then we want to do probability x equals 1. So every x is going to get a 1. Now, x equals 0 is a really chill one because anytime you do n choose 0, you just get 1. So that entire thing disappears at the start. Then anything power 0 is 1. So again, that's going to disappear because it's all multiplication here. And so finally, you're left with 1 minus p. So you have 1/10. And that's going to be the power of n minus x. So if x is 0, then you just got 1/10 to the power of 4 there. Which then just simplifies, but for now we'll just leave it there. As for x equals 1, that one always ends up being n. Yeah, I won't let you... You can take that for granted later, but because that's a thing that's probably common to forget, what I'll do is I'll just expand these out as if you had to do it by hand. So if n is 4, that means you have 4 factorial, which means you do 4, 3, 2, 1. If n is 4 and x is 1, that means you got 3 factorial down there. So you got 3, 2, 1 times x factorial. So 1 factorial is just 1 again. Cross, cross, cross. You're left with 4, which is n. So basically any n choose 1 is always just n. So leave that as 4. P was 9 out of 10. So you got 9 out of 10 to power of 1 since x was 1. Then you got 1 out of 10 power of 3 since you got 4 minus 1 for your power there. Then from there, it's the addition of these two things. So you're going to have probability x less than 2 is equal to, what was the earlier one? 1 out of 10 to the 4 plus 4, 9 out of 10, 1 out of 10 to the 3, which looks really, really nasty. One of my favorite things to do for favorite way to solve a thing is to do factorization where possible when you have these stupidly big indexes. So we can see there's a common factor of 1 over 10 to the power of 3. So I would just go take that out the front. And then that way, when you're doing this math on the inside, it's much easier because now you've got the 1 out of 10 remaining from this. You've got this whole thing disappeared, so now you just got 4 by 9 over 10. So 36 over 10. 1 over 10, 3. So we've got 37 over 10. You could even go a step further and take out another common factor of 10. So 1 cubed is obviously 1, 10 cubed is 10 cubed. Taking another 10 out, you've got 1 over 10 to the 4 times 37. So you've got 37 over 10 to the 4, which, just 10 with 4 more zeros attached to it. 37 over, I'm just thinking, the common factors, the reason why this is a better way of going about it is because you don't really want to have a massive fraction and then think, how do I simplify it? So one of the things I was thinking of doing before expanding this was to do a prime factors thing, like bring this down to prime factors, bring this down to prime factors, and see where we go from there. But the factors of 10 are 5 and 2, and the factors of 37, well, I can tell you they're not going to be 5 or 2. So because they don't share common prime factors, I'm happy to now expand this out knowing that it's not going to simplify any further. 10,000. Let me just double check the answer to make sure I didn't do anything stupid. Yeah, they even left there as an index form actually. 37 to over 10 to the 4. Sweet. Alright. I hope at the very least the way that I did that was enlightening, because if you expand the indexes here, you're in maybe not the end of the world, but doesn't really feel great. Anything to clarify further there? If not, have a read of the next question. Question 5. Oh, wow, that zoomed out real far.
Chris, is the answer to question 5A 600 people?
Probably. Did you just sub in t equals 4 for that?
Yeah.
Yeah. So the scenario is essentially, if h of t is modeling the population after t years, then 4 years means t equals 4. H is the population, so when you sub in t equals 4, you just get 3,000 over 5, which, yeah, 600. Easy. Next up, unless any questions, of course. A new function h1. Yeah, I'll let you guys try to digest what's going on in B. They like to do these things where they redefine functions that are the same function but different domains. Or sometimes just different functions, but I don't really read too much of it. Let's see how you go with interpreting at least what's going on. There's a bit going on in this one. But we don't have any like concrete next steps, maybe some concepts. What kinds of concepts are coming to mind based on the keywords?
Chris, I'm kind of confused with the wording
Yeah.
because I've really seen these questions before. So could you like sort of work through it?
Yeah, no, certainly. All right, let's break down into some. So, like the obvious key information is going to be like your letters and numbers, right? So we have this statement here, h1 of 0 equals h of 0. I'll give this one for you, which is h1 is just a new function, right? We don't know what that function is just yet, but it is some new function. So with that in mind, h1 of 0 being equal to h of 0, what does that actually mean? Like, what's mathematically being said there?
If you sub in 0, you get the same answer.
Correct.
So
yeah, no, absolutely. If you sub in 0 into either function, they will be the same y value. Nice. That's one piece of information that matters. h1 decreases at half the rate of h. So when we think about rates of change, right, decreasing at half the rate, rate of decrease, what kinds of concepts come to mind when it comes to rates of change? Concepts, functions, equations, anything that comes to mind there? Rates of change has to do with slopes. I'll say that much.
like derivatives.
There you go, derivatives. Yeah, nice. So derivative is an equation that tells you the rate of change of the original function for at any given point in time, which is what this one's saying, right? Rate at any point in time. So far we know they share the y-intercept, because x equals 0. And we know that the derivative of h1 will be half that of the derivative of the original. All right, that's what that's saying, decrease at half the rate. So based on some of these things that we've been talking about, what would be useful next steps to take from here? Got two pieces of information we can use. One is they share the y-intercept. The other is derivative of h1 is half the derivative of the original. What should we act on first? Doesn't really matter which one you do. All right, that's right. I'll get this one started. I would personally just go for derivative thing first, just because h10 equals h0 is kind of tough. I mean, you can assume it's still going to be a hyperbola, but that's a bit tougher to work off of. But since derivatives matter, one of the things you can do as as a simple next step is to just do the derivative of your current function. So if we know h of t is currently 3000 over t plus 1, then derivative of that is, well, maybe we should rewrite this to make it a bit easier. We'll use our negative indexes, although technically you don't need to. It just makes it easier to see that this is in fact a chain rule type thing. There we go, that's better. So negative comes out the front, negative 3000. Def of this inside is just 1, so I'm just going to not bother with it. And then that. That's our derivative. Now, the statement was h1 decreases at half the rate of h. So essentially, h1 dash of t is half of h dash of t. Negative 1500 t plus 1 power negative 2. So that gets us that. Then from there, we still care about getting h1 because overall we're trying to do a statement of transformations. So we need to figure out, what is h1? If we're trying to figure out how to get from h to h1, we need both of those equations. When you have the derivative of h1, how can you get back to h1, sorry.
Anti-differentiate?
Anti-diff it. Nice. That's it. So h1t is the anti-diff of h1 dash t. Anti-diffing this, we've done an anti-diff of this kind of thing before. So h1 of t is just, so you're going to have negative 1500 on where was it again? Some of this particular anti-diff always screws me a bit. A, and yeah, okay. In fact, yeah, just so you guys can follow along, I'll pull up on the PDF as well if you want to see. I'm following the AX plus B thing. So in this case, our A is 1. We're doing n plus 1, so it's going to get us to -1 down here. T plus 1 is going to remain the same, -1. But then we're going to have this plus C because we're doing anti-diff. Let's not forget that. So looking at having 1500 on T plus 1 plus C after we've removed the integral. I know we are heading time, so if anyone needs to be somewhere, feel free to head off, but I'll finish this one for everyone else. And it'll be on the recording too, so don't feel like you'll miss out. But okay, so that gets us h1 of t, or at least a lot of the way to h1 of t. There was some other key piece of information that we haven't used yet, and it'll be useful in getting us h1. What should we do?
Should we sub in the x and y value? We know the x and y value at h of 1 equals 0. Do we sub that in to find c, or?
Say that again, sorry? It is going to be a substitution. I just wanted to check the numbers were there.
So we know that like at h1 of 0, it equals h of 0, so we know the x and y value at that point.
Yeah, correct. Yeah, so we just need to figure out h of 0, and then that way we can, which h of 0 is just 3000. You're just doing 3000 over 0 plus 1. So basically, if I sub in 0 on this, I should have 3000 equals 1500. Yeah, still 1500 plus C. So 1500 plus 1500 is going to get us 3000. So in total, h1 of t is equal to 1500 on t plus 1 plus 1500. We're trying to get 2 here from h of t is equal to 3000 on t plus 1. You could do the whole x dash y dash stuff to do a point form on this to get from here to here. That's a lot of effort to get there. Just to be brief, we can see the key differences are going to be, well, I'll let someone else point it out. What are the key differences as far as transformation factors?
Translated up?
Yep, that's one of them. There's another difference.
I can't quite remember like the terms, but like the top value has been halved.
Yeah, correct. So that's going to be a dilate factor, specifically dilate from the x is that one. And so yeah, in order, you want to do DRT when you're doing it this way, when you're just kind of looking at the functions and seeing how they go. The reason why is because dilates are multiplies on the entire thing. So for instance, if I put a 1500 here first and then multiplied everything by a half, I would actually take my 1500 and halve it when I don't want to. So in order, you would do your dilate from x as factor half, and then you do your translate vertically or up as 1500. There's going to be several different ways you can do this. That's one of the fastest. Yeah, that's about it really. Cool. If anything.
Is there any, like, there's probably not, but just wondering, is there any possible way to do it without actually finding what h1 of t is, or is that the only way you can do it?
Yeah, it's definitely the way that I'm checking the answers now. It's definitely the way the answers did it. Because fundamentally, to figure out where you're starting, where you're going, you need to know both of those things. And in simpler things, rates of change doesn't necessarily need derivatives. Like if you have linear, for instance, rate of change is just the gradient. And so you don't need to bother with derivative. You just know, oh yeah, cool. If my first linear had a gradient of 4, my second linear has a gradient of 2. So in simpler circumstances, yeah, you could skip the whole derivative thing and just use your intuition around that. For exponentials, I think, now, maybe don't quote me on this one properly, but base rate of base rate of growth of exponentials is based on the, I said base a lot, but it is based on the base, right? So like the basic rate of growth of an exponential is its base. Like for instance, 1.05 to the power of x has a 5% growth rate. And so if you get really nuanced with your exponentials, maybe you can say, okay, I kind of already know my growth rate's 5%, so the growth rate of the next one should be 2.5%. That I'd have to look into a lot more though to really be confident with that, but I can imagine something like that is doable. So in short, derivative is probably the easiest way.
Okay, cool. Thank you.
No worries. All right, if there's nothing else, I'll let you enjoy the rest of your day.
Thank you. Have a good night.
You too. Take care.